All right, folks, here's a recap on today's lesson. We were working with the trapezoidal rule, okay? And basically, let's look over at this example over here. So if we were to look at this curve over here, x squared, and we used to approximate the area using left ram, right ram, and mid ram, and now we're going to add in trapezoidal rule, okay? So if you look at these red trapezoids here, okay, if you look at the red trapezoids over here, now you can see that we have a red trapezoid here, 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 and there's supposed to be one more to the right here, okay? Now these lines are not going to these are straight lines over here, for example, from here to here, okay, and they're not supposed to perfectly overlap the curve. In fact, they're either going to be underestimates or overestimates. You're going to see that in this case, it's going to be an overestimate. Okay, so here it is. When you look at the blue here, that's left ram. Okay, when you look at the green over here, and the green should come down right here. When you look at the green, that's right ram. Okay. Now, FYI, looking forward, the trapezoidal rule of approximation is always going to be the average between left ram and right ram. Okay, it's always going to be the average between the two. And one way of reminding yourself that is that you can see this red diagonal line cut this rectangle right here. Okay, this rectangle right over here. Okay, let me use a better one. Okay, you can visually look. This is just a visual test. It's not 100%. Okay, you can see this remaining piece gets cut in half. Okay, so you can see that you can use that to rationalize and remember that trapezoidal rule is always going to be the mid or the average between the left ram and right ram. Okay, so anyhow, let's pull these squares aside, these left ram and right ram. Okay, and let's use the formula. Okay, now at this point, I'm just going to have you trust in the formula. If you guys are really curious on how the formula came to be, I can show you. There's a proof for it. Okay, just come after school and I can show you. But let me just show you how this formula works. So just FYI, okay. This this is going to be the height if you turn your head left like a confused dog 90 degrees. This is going to be height of the trapezoid. This is going to be base 1 and base 2, just so you can really associate what goes what with the trapezoid. But in terms of these variables, it's pretty straightforward. Okay. Now it's asking for the estimation between 1 and 2, okay? Between 1 and 2 right here, okay? Between 1 and 2. So between 1 and 2 is right here. And it's saying to partition it into 4, okay? 1 and 2 was actually right here. Okay, that's basically or sorry, right here. Wow. Okay. So it's basically telling you to partition of 4 parts. So 1 and 2, the distance between 1 and 2 is 2 minus 1, which is 1. Partitioning it into 4 trapezoids means 1 divided by 4. Okay, so again, the distance between 1 and 2 is 1 because 2 minus 1 is 1. Partition this distance of 1 into 4 parts, you get 1 over 4 per partition. So that's why you get this 5/4, 6/4, 7/4, because you do 1 plus 1/4 is 5/4, plus another 1/4 is 6/4, plus another 1/4 is 7/4. So those are your x values for each partition. And remember, 1 can be rewritten as 4 over 4. So now, first of all, these are always going to be constants, 1, 2, 2, 2, 1. So the n over here, it's going to be 1, and then the ends of this. The gray highlights the gray highlights within the parentheses, the leftmost gray highlight and the rightmost gray highlight, the coefficients are always going to be 1 and 1, and everything in the middle is going to be 2. Okay, all the coefficients are going to be in the middle are going to be 2. Now, it just so happened, or excuse me, it doesn't always have to be 3 2s. It can be as many 2s as needed. And I'll tell you this: the number of 2s in the middle is always going to be 1 less than the number of partitions. So if there's going to be 4 partitions, it's going to be 3 2s, so 2 2 2. If there's 6 partitions, there's going to be 5 2s in the middle, 2 2 2 2 2. Okay, and remember, the coefficients on the leftmost is always going to be 1, and the rightmost is going to be 1. And now you're just going to plug in the y values. Okay, plug in the y values. So let's ask ourselves this: what is let me erase some highlights over here. What is 1 squared? It's 1, and we plug that in for y0. What is 5/4 squared? That is 25/6/16, which we plug in for y sub 1. What is 6/4 squared? Okay, that's y sub 2, which is 36/16. And lastly, what is 7/4 squared? That's 49/16, which we plug in for y sub 3. And it's not lastly, that was second to the last. What happens when we plug in the x value of 2 into x squared? We get y sub 4, which is 4, because 2 squared is 4. So now we took care of what the parentheses is. Okay, let's take care of this h over 2. H is always going to be the distance between the upper bound and lower bound. And in this case, the upper bound and lower bound distance is 2 minus 1, okay, which is 1, divided by the number of partitions, which is 1 over 4. So h is going to be 1 over 4, and that's shown over here. Again, 2 minus 1 divided by 4 gives you 1 over 4. And when you do 1 over 4 divided by 2, you can think of that as times. Divided by 2 is the same thing as times 1 over 2, and you get this 1 over 8 right here. Okay? And now we filled in all the terms and variables into our formula, and now this gives us 2.34, which is our estimation. Okay? Now we contrast that now. What we can do is we can evaluate this integral right here by taking the antiderivative of x squared and then plugging in upper bound minus plugging in of lower bound. And we're going to see that it's going to equal to 2.33. Let me see if I can pull up. Okay. Let me see if I can pull up over here. I think I can pull it up quickly over here. It is 6.5. Let me pull up that example. Bear with me, it is right over here. Okay, so let me pull that up here and go here. Okay. Now, if you look right here, okay, I took the antiderivative, I evaluated this integral right here by taking the antiderivative, okay, of x squared, and I got x cubed over 3, evaluate it, and I get 7 over 3, which becomes 2.3 repeating. Okay, so this is the actual area, this is the estimation, so we can see this is an overestimation. Okay, so this estimation was overestimated because this is greater than this. Now, as a rule of thumb, when the graph is concave up, which is what it looks like, then it is going to be, your trapezoidal rule estimation is going to be an overestimation, and vice versa. If this graph is concave down, your trapezoidal rule is going to be an underestimation. Now, we know this is outside of, we can visually see this concave up, but to really confirm that it's concave up, take the derivative of this, which is 2x, take the derivative of that, which is 2. Okay, so again, the first derivative of x squared is 2x, the second derivative is 2. 2 is greater than 0, which means it's concave up. Okay, again, if your second derivative is positive, then it's concave up. And since 2 is greater than 0, it's positive, which means it's concave up, which means your trapezoidal rule is an overestimate. Okay, concave up means it's an overestimate. Now, you can stop the video right here and you will have enough tools right now to do Riesz problems, the problems assigned over here, okay? However, I want to show you guys these examples right here, okay? So we can see, let's see, I actually might make a separate video on these for Monday because we don't, yeah, you know what I'm going to do? I'm going to make a separate video. I'm going to do it. I'm going to push it till later on to do these examples over here. Yeah, I'm just going to do that on Monday, on Monday, the next class. Okay, thanks for tuning in, folks. Appreciate you.